All right, first thing I'd want to do is put the data in, and so we got 0, 2, 3, and let's let our y be equal to what did we get? 2.1, 7.7, 13.6, and 27.2. Okay, now um, what we do next is I don't know, as you probably would imagine, we're going to set up our quadratic model, and we're going to do a linear model, and I want to set up y tilde x, which would work if I wanted a linear model, but in this case I want an exponential model. Okay, that's not going to work, because that's going to think that's x plus x squared. It's going to think, okay, what I've got to do here is I've got to set this so it separates it as an operator. Yeah. So guys, our quadratic model. Yeah, okay, cool. It's exactly what we got through least squares. Now, you know the way mathematics works, right? We look at at specific examples, and then we seem to want to generalize the heck out of everything. And so that's what I want to do here. Ultimately, again, we calculated k plus 1 partial derivatives. And the partials would be, of course, partial of q with respect to beta 0, partial of q with respect to beta 1, up to the partial of q with respect to beta sub k. And so if we think this through, looking at the first partial, we're going to have the following. So b0 times n plus b1 equal 1 to n x sub i's plus beta sub k 1 to n x sub ik equals the sum of our y's. Second guess myself. Yeah. Okay, that's good. Now the next are going to increase by a factor of x sub I. So here we'll have actually x sub I equal 1 to n plus beta 1 1 to n x sub I squared plus beta sub k I equal 1 to k 1 to n x sub I k plus 1, and then we have to account for that extra x sub I term. Out here. Now guys, let's again generalize this. So we're ultimately, our first term is going to be b0 times 1 to n of x sub I to the k power plus beta 1 and the sum of I equal 1 to n of x to the I to the k plus 1 power plus beta sub k I equal 1 to n of x to the I to the k plus k, so that'd just be 2k. And that's going to be equal to, got it, run out of space here. Well, let me just try to squeeze it down here. Well, I've done a great job. I've been sitting here talking and you guys haven't even been able to see what I'm doing. All right, so let's go back. I feel like I wasted your time. So what we're doing here is just looking at the k plus 1 linear equations here that would be the partial derivatives. And what I'm trying to do is squeeze this last term in at the bottom, which would be I equal 1 to n x sub I to the k power to y sub I. So guys, for k equal 2, we would have beta 0 sum equal I from 1 to n of our x sub i's plus beta 1 sum equal I equal 1 to n. Oh, wait a minute. Getting off here, haven't I? Yeah. Scratch this. So I've got beta 0 n plus beta 1 sum of the x sub i's. I'm going to leave this subscripts off because I think we've all got that taken care of. So beta 2 sum of the x sub I squared will be equal to the sum of our y sub i's. The second we have will be beta 0 sum of our x sub i's plus beta 1 sum of our x sub I squareds plus beta 2 sum of our x sub i's cubed. So it's going to be the sum of our xi, yi's. And then finally we'll have beta 0 because we're going to have k plus 1 partials. So we'll have x sub I squared plus beta 1 sum x sub I cubed plus beta 2 sum x sub I to the 4th power, and guys, obviously this is going to be our x sub I squared times y sub i's. So we also could have solved this by, we know that n in this case was 4, so we could have creatively had 4 there. The next thing we could have looked at is we could have looked at the sum of the x sub i's Well, that's a really easy one. Watch me miss it. So the sum of the x of i's would be 6. So guys, we could come in. And have this times 6. And the next thing we could do, darn it, is we could come in and look at the sum of the x of I squared, which would be so we got 9, 13, 14. So guys, the first would be equal to 14. And we're on a roll here, so let's just go ahead and sum up our y sub i's. So sum of our y sub i's. I forgot my data set. Okay, so we've got 2.1 plus up to 27.2. Yeah, I need to get my calculator on that one. Yeah, 50.6. So guys, the first thing, that we have here could be like that. And guys, clearly we could go through, it'd take a little bit of work. And I'm not going to have time to do that in this lecture, but we could clearly go in and take care of some of this other stuff. Well, this is going to work out nicely because the sum of the x of i's we already know was equal to 6. And we already know that this is 14. And we could go ahead and finish this out. And ultimately, we're going to have very similar to what we had before, but it's going to be factored down. I can't remember exactly what we did actually get before, but so anyway, I guess we had 101.2, so 8, 12, and 28. So you can see what we had before. In this one right here, I'll put it in blue. Kentucky blue, guys. Before we had, yeah, how about if I give you something you can see? Let's go with yellow. So before we had 8 beta 0 plus, I've lost it, 12 beta 1 plus 28 beta 2. And we had 101.2, wasn't it, I think? So guys, we can clearly see the connection from this to what we had. So again, just a different version of quadratic of the partials that we end up getting. So and some people think it's easier. You can easily program your calculator or whatever to come up with these values. And it wouldn't be hard at all. So anyway.